All right, we'll start off talking about organometallic chemistry with talking about CO, which is a very common ligand, carbon monoxide, as well as we'll dip our toes into talking about simple alkene ligands. The carbonyl ligand forms a huge number of complexes with different metal ions, mostly in lower oxidation states. Low oxidation states being 0, +1, +2, and even some negative valent oxidation states where the metal has a negative charge, like -1 or -2. Here's a simple complex, chromium hexacarbonyl. We have a chromium 0 center there in the middle, and we have 6 cyanides around it in an octahedral arrangement. Or iron 0 here with 5 carbonyls attached. The center right there in the middle is iron. And then we have 5 carbonyls. This is a perfect trigonal bipyramid. And then finally, nickel here. We have a nickel 0 center with 4 COs around it in a perfect tetrahedral arrangement. And you might wonder naively why nickel has 4 COs, iron has 5 COs, and chromium has 6 COs. Well, it ends up that these obey something called the 18-electron rule. And that means if we sum up the d electrons on the metal center plus the electrons that come from the ligands, for organometallic complexes like these, we almost always get a total of exactly 18 electrons. And so here's how this works out. So nickel 0, if you look at it, it's in the 10th column. It is a D10 electron configuration. So there are 10 electrons from the nickel 0 center. And then each CO, the carbon of each one of those COs has a lone pair. And so 4 times 2 from each one gives us 8 electrons from the carbonyls. So 10 plus 8 gives us 18. Iron 0 here comes in with 8 electrons. It's in the 8th column, and therefore it's only bringing in 8 to the total, so we need to bring in an additional CO. So now we need 5 COs to bring us up to 18 electrons. And then chromium 0 is just a D6 metal, so we need a total of 6 COs to bring in 12 electrons to bring those up to 18 electrons. The metal can be more complicated, so I don't want to imply that they can only be these 0-valent metals. But obey the 18-electron rule, many carbonyls will form anions or cations, such as vanadium. Vanadium 0 is a D5 metal. When it accepts an additional electron, it becomes a D6 metal. Vanadium with a -1 charge brings 6 electrons, and then 6 COs bring in 12 electrons for a total of 18 electrons. Again, the vanadium has a formal oxidation state of -1. Here we have manganese. The whole complex has a plus charge. The carbon monoxides are neutral, and therefore this is manganese +1. Manganese +1 is also a D6 metal. Plus 6 CO ligands, that's 12 electrons. 6 plus 12 gives us 18 electrons. Again, formal oxidation state of manganese now is +1. And we can even have these dianions. So we have iron here with a 2- charge, which is a D10 system. Iron 0 is D8. Iron 2- becomes D10. 10 electrons from the metal center plus 4 COs to give us 8. 10 plus 8 gives us 18 electrons. Again, here just on this one side, we have vanadium with a -1 charge. We have manganese with a +1 charge. And we have this iron center with a -2 charge on the iron. The formally charged ligands contribute to the charge on the metal center. And so we have, for example, this is a neutral complex, but the pieces inside are not neutral. So this complex has a chloride and a manganese with some charge, and then the COs are neutral. And so this must be manganese 1 to counteract this minus charge from the chloride. So we have a manganese 1 center, which is D6. 5 COs bring 10 electrons, and then 1 Cl minus brings 2 electrons for a total of 18 electrons. These metals are very electropositive, so when they're attached to hydrogen, it is present as a hydride. It's present as H minus, hydride. And so we have H minus and another H minus. So two minuses from the ligands. COs are neutral, and so this is iron in the +2 oxidation state. Iron 2 is D6. We add to that 4 COs for 8 more electrons, 2 H minuses for a total of 4 more electrons. So 6 plus 8 plus 4 gives us the 18 electrons. And then finally, again, when it's attached to any of these transition metals, it's present as hydride, H minus. So we have H minus, which makes this cobalt +1. Cobalt +1 is D8, plus 4 COs to bring in 8 more electrons, plus the 1 H minus brings in 2 electrons. So 8 plus 8 plus 2 gives us 18 electrons. We right away get into some strange ligands, though. So everything that we talked about from coordination chemistry, we had lone pairs. Well, it ends up for these organometallic complexes that a pi bond can also act as a ligand to a metal center. And so here we have ethylene, C2H4, and there is a there's a carbon-carbon double bond between the two carbons. The pi part of that double bond can donate to the metal center and act also as a 2-electron donor to a metal center. And let's do some counting for this then. We have tungsten, and we haven't figured out the charge yet, but the COs are all neutral. Ethylene itself is also a neutral molecule, so 5 times 0, so no charge from any of the ligands. The whole complex is neutral, so this is tungsten 0. Tungsten is in the 6th column, so tungsten 0 is D6. The 5 COs contribute 10 electrons, and then the double bond of the alkene here provides 2 more electrons to bring us up to 18 electrons. So each CO, the lone pairs are interacting as 2-electron donors, and the pi bond of the alkene is also acting as a 2-electron donor to bring us up to